Violating the Liskov Substitution Principle makes our programs difficult to reason about, which might lead to bugs that are hard to find, which makes our systems difficult to change. Allow me to explain the 7 rules that make up the Liskov Substitution Principle. The principle essentially states that it should be possible to use an object of a subtype wherever an object of its supertype is expected, without altering the correctness of the program. In other words, without leading to unexpected behavior. But wait, you might say, isn't that problem already solved by compilers? By type checking? Well, yes and no. It is entirely possible and actually quite easy to write programs that violate the Liskov Substitution Principle. The principle consists of 3 type rules and 4 behavioral rules. The 3 type rules are usually enforced by compilers, by the type checker. But these behavioral rules have to be respected by us as developers, and if we break them, then we will violate the Liskov Substitution Principle and again run the risk of creating systems that are very difficult to reason about. So in a statically typed language like C# or Java, it isn't really possible to violate the type rules, but it is certainly possible to violate the behavioral rules. Let's understand the Liskov Substitution Principle by first looking at the formal definition, then the Robustness Principle, then the type rules, and then the behavioral rules. Let's go! So here's the formal definition. Let P of X be a property provable about objects X of type T. Then P of Y should be true for objects Y of type S, where S is a subtype of T. This isn't actually too complicated. We have 2 types, S and T, and S is a subtype of T. And when we here say X and Y, we are talking about objects of these types. And what this principle states is simply then that if you have an object X of type T and something, P, is true about that object, then that should also be true about an object Y whose type is S, because S is a subtype of T. So in other words, whatever is true about objects of the supertype must also be true of objects of the subtype. In other words, the subtype needs to respect the contract of the supertype. Objects of the subtype need to behave in a way that is consistent with the way that we expect objects of the supertype to behave. In a sense, that is all there is to it. But in another sense, it isn't all that trivial to define what it means to not behave unexpectedly. And this is why we end up with the 3 type rules and the 4 behavioral rules. But I find that the simplest way of remembering the gist of these rules is to consider what is known as the Robustness Principle, also known as Postol's Law. It was originally formulated for the specification of the protocol TCP, but it serves as a great mnemonic, as a great reminder for the rules of LSP, Liskov Substitution Principle, and of type-safe variants. Here's what the Robustness Principle says. Be conservative in what you do, but be liberal in what you accept from others. So we should make sure to not make mistakes ourselves, but we should forgive the mistakes of others. One way of thinking about the Robustness Principle is that it essentially says that we should be contravariant in input and covariant in output. And that means that if you have a type that is a subtype of another type, and this subtype has an instance method which is also defined in the supertype, then that method should be liberal in what it accepts from others. In other words, it should accept whatever the parent accepts or more. Look at this visualization. Here we are depicting the set of possible values that the supertype accepts. And then we are saying, for the subtype to be a valid subtype of this supertype, in other words, if we're going to follow the Robustness Principle, the instance method in this subtype needs to accept either what the supertype is accepting or more. A bigger set, a superset. Right? Notice how the set of possible values that the subtype can accept is bigger than the set of possible values that the supertype accepts. This is contravariance. Conversely, If we look at the other side, if we talk about output, and we are talking about covariance, then if the subtype is to be a valid, a reasonable subtype of the supertype in accordance with the robustness principle, then the subtype should be conservative in what it sends, in what it produces as output. So our instance method should only return values that are included in the set of possible values that the supertype can return, or something smaller, a subset of that set. So the possible values that the subtype can return is a subset of the possible values that the supertype can return. For the output, that's covariance. That's being conservative in what you send. But on the input side, the subtype is the bigger set. The instance method in the subtype can accept more values than what the instance method in the supertype can accept. The set of possible values in the subtype becomes a superset of the set of possible values in the supertype. That's contravariance, or being liberal in what you accept from others. If all of this variance shenanigans feels confusing to you and you haven't watched my other video on covariance and contravariance, then I highly recommend that you pause this video and go check that video out. It is crucial to have a good understanding of contravariance and covariance when we're trying to understand the type rules and behavioral rules of Liskov Substitution Principle. So pause and check out that other video. Okay, let's talk about the type rules. In order to adhere to the Liskov Substitution Principle, we must follow the following 3 type rules. 1. Method parameters must be contravariant. In other words, if you have an instance method in the subtype, then the parameters of that method needs to be of the same type as the ones that we have in the instance method in the supertype. Or they need to be supertypes of those types. They need to be more general, because again, the subtype needs to be liberal in what it accepts. 2. Our method return types needs to be covariant. In other words, if we have a method in the subtype, then the return type of that method needs to be the same type as the return type of that method in the supertype. Or it needs to be a subtype of the return type in the parent. Because again, the subtype needs to be conservative in what it does, in what it sends. We need to return values from the same set or from a subset. We need to be covariant. So if you have an understanding of covariance and contravariance, then rules 1 and 2 should make perfect sense to you. And if they don't, again, check out my other video that specifically talks about contravariance and covariance. So contravariance in input means that a method in the subtype can accept a type which is more general than the type which is accepted in that method in the supertype. And covariance in output means that the subtype can return a more specific type than the type that is returned in that method in the supertype. What about the third rule? The third rule says that we must not introduce any new exceptions, and that all exceptions that we throw must either be of the same type as exceptions that are thrown in the parent, or subtypes of those exceptions. Because again, remember, in general, the idea is that our subtypes must respect the contract of our supertypes. And if our subtypes suddenly could throw entirely new exceptions, then anyone using an instance of the subtype as if it was an instance of the supertype would get very surprised when suddenly there is an entirely new exception thrown that the supertype never told us about. So exceptions in the subtype need to be of the same type as the exceptions in the supertype, or subtypes of those exceptions. That's it for the type rules, and again, these rules can and are enforced by many compilers, by many type checkers. Not all languages enforce all rules, but in theory, the languages could enforce all rules. Let's move on to the behavioral rules. Number 1, the preconditions in the subtype need to be the same or weaker than the preconditions in the supertype. Number 2, the post conditions need to be the same or stronger. Number 3, the single state invariants need to be the same or stronger. And number 4, the multi-state invariants need to be the same or stronger. Let's unwrap this terminology. The preconditions of a method defines what must be true before the method can be called. For example, a method that takes an integer might require that we pass it a positive integer or a non-negative integer. And this is a good time to pause and reflect between the difference between the type rules and the behavioral rules. Notice how this precondition can't easily be captured as a type, which is why when we were talking about the robustness principle, we were talking about values and not about types. So now we're saying that a method that accepts an integer might not actually accept all integers. It might accept a subset of all integers. And which subset of all integers it accepts matters when we want to subtype that type. So the subtype needs to respect what subset of the integers its parent is accepting. So in a sense, the type rules are operating on the type level and the behavioral rules are operating on the value level. Okay, what about postconditions? The postconditions of a method defines what must be true after a method has been executed. For example, a function that returns the absolute value of an integer must never produce a negative number. So we might say that the postcondition for that function is that when it has been executed, the returned number is not negative. Okay, what about invariance? We have single-state invariance and multi-state invariance. The single-state invariance of a class defines what must be true of objects of the class at all times. For example, a class with an instance variable of type string called name might require that that instance variable, that string, is always longer than 3 characters. For example, invariance may be violated temporarily when a method is being executed, but when you exit the method, the invariance must again be true. What about multi-state invariance? The multi-state invariance of a class defines what must be true over multiple states for an object of that class. For example, a multi-state invariant might require that some particular integer is always incremented but never decremented. It's always increased but never decreased. Formally, we express preconditions, postconditions, and invariance as sets of what are called predicates, logical statements that are either true or false. And this terminology is also used in the context of design by contract. Check out the links in the description for more resources on that. It's a very interesting topic. Okay, but with the terminology out of the way, what are the 4 behavioral rules actually saying? Weaker preconditions and stronger postconditions is the same idea as contravariance in input and covariance in output, but at the value level rather than at the type level. So the subtype can have weaker preconditions but not stronger preconditions, because it needs to be liberal in what it accepts from others. It needs to be weaker in what it demands from others. Or of course the same. And the postconditions in the subtype can be stronger than the postconditions of the supertype, because we should be conservative in what we send. So we should either send values from the same set as the set that we're sending values from in the supertype, or from a smaller set. Our postconditions can be stronger, but we can't have weaker postconditions, because that would mean that we would be able to send entirely new values, values that we would not expect from objects of the supertype. Let's understand why these 2 rules have to be true by inverting them. If it was possible to make preconditions stronger, not weaker, but stronger, then objects of our subtype cannot safely be used where we are expecting objects of the supertype, which is the whole point of Liskov Substitution Principle. It's the whole point of substitutability. Imagine, for example, that we are building a hierarchy of collection types and that our supertype is called list. Then imagine that the list has an instance method called add, and that add has a precondition that specifies that the item that we're trying to add must not be null. If we were allowed to make the precondition stronger, then it would be possible to create a subtype called unique list, with a precondition for the add method that specifies that the item that we're trying to add must not already be in the list. But this means that we would lose substitutability. We we would no longer be able to use objects of the subtype where we are expecting objects of the supertype, because the supertype does not say anything about forbidding trying to add the same item twice. So we can't all of a sudden just introduce that condition in the subtype. This is what we mean when we say that the subtype shouldn't behave unexpectedly or incorrectly. It doesn't respect the contract of the supertype. Similarly, if it was possible to make post conditions weaker, then again, an object of the subtype can't safely be used where an object of the supertype is expected. Imagine again that we're building a hierarchy of collection types, and that our supertype, called list, has a method called clear. Then imagine that the post condition of the method clear states that when clear has been executed, the length of the items in the list will be 0. If we were allowed to weaken the post conditions, then it would be possible for us to create a subtype of list called, for example, immutable list. And clear in the subtype, in immutable list, doesn't actually clear the list because it is an immutable list. So whatever items are in the list are in the list. So again, that means if we have an object of the subtype, then we can't safely use that where an object of the supertype is expected. The subtype violates the contract of the supertype. Because if all we know is that we have a list and we call clear on that list, then we assume that the length of the list will be 0 after we have called clear, because that is what the post conditions of the supertype state. But since we have weakened the post conditions in the subtype, we no longer have this guarantee. So if it happens that the runtime type of the list that we have is actually an immutable list, then when we call clear, the length won't actually be 0. And again, we end up with surprising behavior. Okay, what about behavioral rules 3 and 4? These state that single-state invariants and multi-state invariants must either be the same or stronger in the subtype. Think of it like this: if something at all times needs to be true in the supertype, then that thing must also be true at all times in the subtype. But if we in the subtype want to make the constraint even stronger, then that is perfectly fine, because the stronger invariant will still respect the weaker invariant. Because whenever the stronger invariant is true, the weaker invariant will also be true. The subtype is respecting the contract of the supertype. Let's go back to our example of collections. If we have a supertype called non-empty list, a list that is never empty and always contains at least one element, that type might have a single-state invariant that states that the length must always be greater than or equal to 1 or greater than 0. If we then create a subtype where we have an additional invariant stating that the length must always be at least 2, then that is perfectly fine, because the invariant in the subtype is stronger. So when an object of the subtype is respecting its invariant, which is stronger, that object will also respect the weaker invariant in the parent. We cannot, however, weaken invariants in the subtype. If we were allowed to make invariants weaker, then it would be possible for us to create a subtype of the non-empty list and change the invariant to say that the length must always be at least 0. But then we are violating the invariant of the parent because we have a weaker invariant. Our constraint is not strong enough. So we would end up with a subtype of a non-empty list that actually can be an empty list, which doesn't make any sense, and again means that we have written code that behaves unexpectedly, incorrectly. So for multi-state invariants, it's the same thing. If say that we're building a list that grows on its own, we might express that the length in the new state is always greater than the length in the old state. In the subtype then, we could strengthen this requirement by saying, for example, that the length in the new state is always longer by 1 or 2. Either way, this is a stronger requirement. It's a stronger invariant. And that is then perfectly fine, because that means that we're still respecting the weaker invariant in the parent. So if the list each time grows by 2, that means still that the list is growing each time, that the length is being incremented and not decremented. So we have a stronger invariant. But again, we can't weaken the multi-state invariant. So we couldn't say that in every new state of the subtype, the length has increased or has remained the same, because that means that we are violating the multi-state invariant of the parent. And again, which puts us in a situation where we're writing code that behaves unexpectedly. So in conclusion, the Liskov Substitution Principle consists of 3 type rules and 4 behavioral rules. The 3 type rules can be checked by compilers, by type checkers, but the 4 behavioral rules have to be respected by us as developers. So Liskov Substitution Principle is not at all a purely theoretical exercise, but has very practical implications for our code. Violating the Liskov Substitution Principle leads to code that is difficult to reason about and that has surprising and unexpected behavior, which might cause bugs that are very difficult to find, and thus means that our systems are difficult to change, which means that we can't keep up with the competition in this ever-changing world and stay in business and grow. So the next time you're about to create a subtype, pause for a moment and ask yourself whether this subtype truly is respecting the contract of its parent. We will all thank you for it. Subscribe.